Started. Hi everybody. My name is Carter Ray. I'm a first-year PhD student at the Université de Montréal, studying under the supervision of Dr. Julie Flavachek-Laurando, who you've already heard speak the other day. So today, I'm going to be presenting the case of a very peculiar high redshift galaxy cluster undergoing an extreme starburst, in our efforts to understand what's actually happening. So as the title of this presentation suggests, we're going to argue that the prodigious stellar formation rate that we observe in this high redshift galaxy cluster is a result of a black hole utterly failing to do its job, with no disrespect to the black hole. So by the end of this talk, I hope to have convinced you of a newly discovered viable mechanism for building up cluster light at the crucial time around cosmic noon. We're going to argue that this mechanism is an uninhibited cooling flow. For those of you who absolutely detest the term cooling flow, just consider it runaway gas cooling. So this work could not have been done without previous efforts by our collaborators, most notably Dr. Tracy Webb's McGill University team and previous students of Dr. Flavachek-Laurando, who are here today, notably Etienne Trudeau. I'd also like to acknowledge the land upon which I work here in Quebec. So L'Université de Montréal is situated on land where, long before the arrival of the French, people of many indigenous nations came together and interacted. And we wish to acknowledge these nations and their descendants in our work. I know that we're on the graveyard shift of this very long, very excellent conference. So if you don't want to listen to me for the next 10 minutes or so, I suggest that you either take a look at the paper. We have the archive link there. We also have a related Chandra press release and a Chandra blog post that I wrote. So with that, let's move on to discuss aging and feedback and cooling flows in galaxy clusters. Thankfully, Julie and Mike have already done the hard work for me. Thank you both very much. You have given excellent descriptions of these. But just to motivate this work a little more, we know that galaxy clusters are the ideal environment for studying AGN feedback and how it quenches star formation to the tame levels on the order of 1 to 10 solar magnitude or solar masses per year that we observe in nearby galaxy clusters today. In this image, this cartoonized image, we can see really nicely the interaction between the hot ICM, which is here in the purplish blue color, and the radio jets stemming from the BCG seen in green. Mike already discussed how these jets and cavities are related. And what we know, what we've been able to do by studying X-ray and radio emission in these galaxy clusters, the community as a whole has demonstrated that these jets are capable of injecting enough energy into the ICM to keep it from cooling in the process that's collectively known as AGN feedback. We see this AGN feedback in nearly all lower intermediate redshift cool core clusters. And even though we know it's to be true at low redshift that this AGN feedback is happening, the question is what happens as we go back in redshift and we approach cosmic noon, so redshift between 1.7 and redshift 2. What happens then? Are we still seeing AGN feedback? Of course, this is a difficult thing to study, but today, that's exactly what we're going to be talking about. I'll be presenting the first conclusive results of AGN feedback, or lack thereof, in a galaxy cluster seen at cosmic noon. So as we move, or as we'll see throughout this presentation, the results were not exactly what we expected. And before we get into the results in this particular cluster, I want to describe the cooling flow problem, or runaway gas cooling, in a very idealized artistic rendering. This video is very, very basic, but it's still very helpful in understanding how these cooling flows work. So what would happen if we had an ICM, and what would happen with the star formation if there was no AGN feedback, if the ICM was allowed to cool rapidly in a runaway form without anything inhibiting it? So let's consider a cool core cluster peaked at this, with obviously a surface brightness peak at the center. In the red, this is the hot ICM. We have the BCG, and red, because it's warm, it will quickly become blue, indicating cold gas. And what's happening is, considering this cool core cluster with peak X-ray surface brightness at the center of the cluster, the ICM is going to emit photons higher and at a furious rate here. The loss of this energy via X-ray radiation is going to cause the gravitational forces to win out, and the ICM is essentially going to collapse towards the center in what's known as a cooling flow, or runaway cooling. It's going to trigger rampant stellar formation, which is expected to be on the rate between 100 and 1,000 solar masses. And I'm sure you all already recognize this is a huge discrepancy between what we see in nearby galaxies today. And this cooling flow problem, as it's known, is usually resolved by invoking AGN feedback. But what happens if the AGN itself is not triggered to create these jets? Would we still see these incredibly prodigious rates of star formation? Actually, it's going to play the video again, so I'm going to pass that. Okay. So now we're going to actually move on to the main object of our discussion today, Sparks 1049, 22.6 plus 5640, 32.5. I'm never going to say that again. It's from now on Sparks 1049. So in this image, I'm presenting to you the combined HST observations of this object. Sparks 1049 itself is a massive galaxy cluster. You see the mass about 3 times 10 to the 14 solar masses at a redshift of 1.709. This has been spectroscopically confirmed several times. So this cluster, to orient you, is sitting really right at cosmic noon, right at the peak of star formation in cosmic history. Sparks 1049 itself was discovered as part of the Sparks collaboration, hence the name, led in part by Dr. Tracy Webb at McGill University using red sequence to identify galaxy clusters. Her team, using optical and infrared observations taken with Hubble Space Telescope and Spitzer Observatory, were able to constrain the star formation rate at approximately 900 solar masses per year. So this is well within the range expected in the cooling flow or perhaps a huge merger. So in this image, there are two kind of crucial pieces I'd like to point out. The first is labeled here. This is the BCG, the brightest cluster galaxy. It's a very stereotypical red and dead BCG, but something we see that's incredibly interesting is what's been identified as a tidal tail, which you can clearly see in the optical. And this tidal tail here, in case the highlighting isn't strong enough, this is intense young stars and young star formation occurring offset from the BCG in a very interesting location. And tidal tails such as these are generally created, or we believe they're generally created, in a wet merger scenario when the gravitational interaction between the BCG and an infalling galaxy strip stars or dust and gas enough to create stars in the wake of that infalling galaxy. So what the team did is they went ahead and took, like I mentioned, they had Spitzer Space Telescope observations. Here I'm showing the 24 micron. And you can see that there appears to be a large amount of star formation seemingly offset. However, the beam is a little too large to say anything conclusively with Spitzer. But due to all this evidence, the authors concluded that Sparks 1049 was likely undergoing a massive burst in star formation due to a recent wet merger. However, it's really hard to come to this conclusion definitively based off these two sets of observations. So we, of course, turn to some follow-up observations. And this is work done mainly by Xray and Trudeau. Now, so we obtained radio data in 2016 using the JVLA in several bands, LX and S. Here we can see the L band contours, which are overlaid in green on the HST image. Note that the emission is not extended in the slightest and shows little to no indication of AGN jets or AGN activity. Sorry, AGN jetted activity. In fact, this emission here is associated with the AGN and it's relatively weak. There's also no indication of star forming or star bursting clumps outside of the core. And bringing together all of this led the team to agree that these findings are consistent with the idea that star formation is not occurring heavily in the BCG, but rather the star formation is really occurring in this tidal tail. Of course, more images were taken. Dr. Tracy Webb and our graduate student Felix Wallen obtained VLA COJ10 data, which are shown in the white contours here, much nicer, tighter beams, so it can actually start to constrain the location of the star formation. And this solidifies the conclusion that there exists a large reservoir of molecular gas that's offset from the BCG. And so bringing all of this information together, the radio and VLA CO data, the idea of a wet merger really starts to fall apart. But to resolve this dilemma and figure out what's actually happening, we're going to turn to the X-ray regime and search for a potential cooling flow, since that would be another mechanism viable for explaining this star formation rate that we see. So in 2017, we obtained 170 kiloseconds of observation with Chandra. And before I demonstrate the X-ray results, let's take one quick look at the optical image and focus on the scale in order to put it in the context of X-ray observations. So if we wish to have the same scale as the X-ray image, we can scale it down. And now with this size in mind, we can take a look at the broadband X-ray image. Here we see the X-ray emission in white, contour starting at 3 sigma level above noise in cyan, and the location of the BCG denoted as a magenta star, and it's approximately to size or to scale. There's two really important features to note in this image. First is the relatively compact morphology of the X-ray emission, and the other is the considerable offset of approximately 40 kiloparsecs between the BCG and the center of the X-ray emission. And despite the fact that this is a distant cluster, and as Mike explained, we don't have a whole lot of counts, we were able to categorize this cluster as a cool core, likely harboring a strong cooling flow. So if we move to this image, we see the HST images again in the background and X-rays as the cyan contours, but this time we're really just looking at the soft X-ray emission. And the soft X-ray emission is again offset by approximately 40 kiloparsecs in the BCG, and moreover, it follows the tidal tail that we see in the optical here, highlighted with this dotted line. So this, together with our evidence that the X-ray emission is associated with a cool core cluster and a complete lack of aging activity, we conclude that we're seeing the buildup of cluster light through an uninhibited cooling flow. If left unmarred, this runaway cooling gas will lead to the creation of the same number of stars as in our Milky Way galaxy, within 100 million years, contributing to the creation of intercluster light. So the natural question of why is this interesting? We can do this by placing sparks in the right cosmological context during the next minute of my talk. So here we're showing the stellar formation rate as a function of redshift for galaxies. We've seen this plot several times. This is for galaxies residing in dark matter halos. You can see that star formation peaks at approximately redshift 2, i.e. cosmic noon. And we can take a look at where Sparks lives, as plotted with this purple line. And it's really right at the peak of cosmic noon, peak of the star formation. Previous studies had demonstrated that the increased star formation was linked to mergers in galaxy clusters. However, through this work, we've demonstrated an entirely new mechanism for the buildup of stars at this epoch and intercluster light, an uninhibited cooling flow. So if in fact the behavior seen in Sparks 1049 is representative of their percentage of galaxy clusters at this epoch, runaway gas cooling uninhibited by aging feedback is a viable mechanism for star formation. My time is up, and I hope I have sufficiently demonstrated the potential a galaxy cluster has to form stars when the AGN at its center utterly fails to do its job.